Okay, so we're going to cover the last little bit of binomials. And as requested, here is your starter joke. Why did the girl wear glasses during math class? Okay, so Mrs. Gaius loves red Skittles, but the last time she got a fun-size bag, there were no red Skittles. The bag was manufactured at the Skittles factory where 10,000 Skittles are made each hour. 20% of the Skittles are red. To make a fun-size bag, 10 Skittles are chosen for each bag. What are the chances of getting a fun-size bag with no red Skittles? So the first thing we need to check here is this a binomial setting? So we use our acronym BINS, right? And so for our binary, do we have a success failure, right? A success would be red, failures would be not red. So we have a definite success and failure, so we meet that criteria. Are they independent? Okay, in this case, the answer would be no. She is not sampling with replacement. So since she is not replacing it, every time she removes the Skittle from the bag, she is altering the probability now for the next one that she's going to choose. So this is actually not a binomial setting. So it does not meet our criteria for that. So now we're being asked to find the probability of getting 0 red Skittles in a group of 10 from the factory if this is not a binomial setting, and to show our work. So we want our probability, right? Our probability that we got no reds, okay? And so remember it said back up here at the beginning, right, that at the factory 10,000 Skittles are made each hour and 20% of the Skittles are red. So if I have 10,000 Skittles, 20% of them are red, so I want the probability I don't get any reds, right? So 8,000 of them are not red times, now I have 7,999 of them that are not red out of 9,999 of them. Okay, and we're going to do that all the way down until I get to 10. Right, so this would be my 10th Skittle here. I'd have 9,991 of them that I'm choosing from, which gives me a probability of 0.1073. Okay, so now as we move on to number 3, it asks us to find the probability of getting 0 red Skittles in a group of 10 from the factory if this were a binomial setting, and to go ahead and show our work. So you can use your calculator, or you could use the formula. You could use your calculator settings or the formula. Okay. In this particular case, if I am using my calculator settings, okay, you need to think about whether you're using binomial CDF versus binomial PDF. Okay, in this particular case, you want 0 reds, so you'd be using your PDF setting. Okay, so my trials are 10, my successes are 0. My probability of success is 0.2, but I'm going to the 0 power with that because I got no successes. My probability of is 0.8 of failure, and 10 minus 0 is 10, so to the 10th power, which gives me about the same answer. Okay, and that's, which hopefully you'll think is interesting, so that you can see that we're going to be able, even if it doesn't 100% fit our binomial conditions, we may still be able to use our binomial formula to calculate the probability. So looking at number 4 here, how do your answers from number 2 and number 3 compare? Okay, they're really, really close to one another. And the reason why that will work is because there are so many Skittles. Because there are so many Skittles, it doesn't really matter when we take one of them away. Okay, so when our probability goes from out of 10,000 Skittles to out of 9,999, okay, it doesn't really matter. That doesn't really impact it when we take one away because there are so many Skittles. Okay, and this is called our 10% rule. And what our 10% rule states is that if the sample is less than 10% of the population, okay, so if the sample for instance, these 10 Skittles, it was my sample, is less than 10% of the entire population, right? Our population was 10,000 Skittles, and I'm sampling 10 of them. So if the sample is 10%, is less than 10% of the population, I can use the binomial equation. I can use our binomial equations as long as my sample is less than 10% of my population. So let's look at this next part here. To ensure that she gets more red Skittles, Mrs. Gaius buys a jumbo bag of Skittles, which contains 900 Skittles. Let X equal the number of red Skittles in a bag of 900 Skittles. Use a binomial distribution to model the situation. Okay, so we're looking for the mean and the standard deviation of X. So she has a bag of 900 Skittles. We said before that when the factory makes 10,000 Skittles, 20% of them should be red. Okay, so our mean here, our mean here is going to be 900 times 0.2, or we should expect to see about 180 Skittles in the bag. Our standard deviation, okay, remember our formula for mean, we saw this today in class, is the sample size times the probability, and our formula for standard deviation is the square root of the sample size times the probability of success times the probability of failure. Okay, oh, I guess I could have actually written out the formula for you. So sample size times the probability times 1 minus the probability, right? Our probability of failure. So in this case, that would equal the square root of 900 times 0.2 times 0.8, which gives us 12. So we have a standard deviation here in this bag of Skittles of 12. So now we want to know the probability of getting at most 150 red Skittles. So now we're looking at the probability that X is equal to at most. So X is less than or equal to 150 red Skittles. Okay, now I'm using my less than situation. So I'm going to use my binomial CDF, and I'm using the less than. So I'm using the CDF, I'm not using the PDF. With my sample is 900. My probability is 0.2, probability of success, right? And my X equals 150, which is going to give us 0.006. If we were to make a histogram of X, what do you think the sample would be? Okay, what do you think the shape would be? So if you were to make a histogram of X, your shape would be approximately normal. Okay, it would be approximately, oh, that was the worst. It would end up being approximately normal. It would be approximately normal because of what we call our large counts. Whoops. Our large counts. And so what our large counts states that if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, we can assume that approximately normal distribution. So, for example, in this instance, right, our n is 900, our probability is 0.2, so 900 times 0.2 is 180. okay, which is definitely greater than or equal to 10. And then we would also check this for n times 1 minus p. So that would be 900 times 0.8. And 900 times 0.8 is going to be 720, which is also definitely greater than or equal to 10. So we can assume that this is going to follow our normal distribution. So we've got our 10% rule here, as well as our large counts. So we can use this binomial distribution as long as our sample is less than 10% of the population. And we can assume normal distribution if large counts are met. And as you go through and do these problems, that's going to be part of showing your work. You're going to have to show that 10%, that you know that 10% rule, if you're using a binomial when it doesn't meet binomial criteria. And then if you're assuming a normal distribution, you're going to have to show this large counts work over here to be able to assume that normal distribution. So now I'd ask you to redo problem number 6 above with a normal distribution and compare your answers. So redoing number 6 using a normal distribution here. So I've got my approximately normal curve here, right? I label my curve. I have a mean of 180, a standard deviation of 12. So there's 180. I'm looking for less than or equal to 150. So I'm looking for that portion on my curve there. Okay, I'm calculating my z-score, which is 150 minus 180 over 12, which is negative 2.5. And then I'm either plugging that into my normal CDF on my calculator, I'm plugging the 150, the 180, the 12 into my normal CDF on my calculator, or I am using my table A, and I should get an area of, what in the world? An area that is approximately 0.006, okay, which is about the same, which is the same as what we got when we did it with the binomial function on the calculator. So our kind of big takeaways from this one, right? So your big ideas, we started to write this down in class, okay, our 10% rule, right? Our 10% rule being that if I'm taking a random sample of size n, so a random sample of size n from population size n, okay, I can use the binomial if my sample is less than 10%, so 0.01 times n, less than 10% of my population. Okay, and then the other big takeaway here is when we can use that normal distribution. So the large counts rule, right, and our large counts being that if those conditions are met, if n times p is greater than or equal to 10, as well as they both have to be met, not just one of them, as well as n times 1 minus p is greater than or equal to 10, okay, I can use a normal distribution to model my binomial. Okay, I can assume that normal and use that normal distribution to model the binomial, right? Remember, that's n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Okay, so ideally, you go ahead and try the check your understanding on your own, and then you can come back and you can check your answer. Okay, so in a survey of 500 U.S. teenagers aged 14 to 18, subjects were asked a variety of questions about personal finance. One question asked whether teens had a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. Let X equal the number of teens in a random sample of size 500 who have a debit card. Explain why X can be modeled by a binomial distribution even though the sample was selected without replacement. So let's kind of go through our acronym here, right? We have our binary part, right? We have our success. They have a debit card. Our failure, they do not have a debit card. Right? Then we need to check for independence. They're not independent because I'm not putting them back in. So when I pull a kid out for the sample, I've altered my probabilities now. However, right, I can use my 10% rule. So 500 is definitely less than 10% of the population of U.S. teenagers aged 14 to 18. So 500 is less than 10% of U.S. teens 14 to 18. Okay, so that works there. And then I do have a set number in my sample, right? 500. And the probability is the same all the way through, right? My probability is 0.12. So so I'm good on the rest of those conditions there. So now number 2, we're using a binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. So we're looking for the probability, right, that X is 50 or less. Okay, and so since I am looking for 50 or less, not exactly 50, I'm going to use the CDF function on my calculator, not the PDF. My N is 500. My probability is 0.12, and then my X is 50. Okay, which is going to give me a 0.093 probability. Justify why X can be approximated by a normal distribution. Well, that's our large counts, right? So our large counts will allow us to justify why we can use a normal distribution on this setting. So to justify that, I need to plug in my numbers. So I need N times P to be greater than or equal to 10, right? So I'm going to have 500 times 0.12, which is 60, right? So 60 is greater than or equal to 10. And then I also have to do my N times 1 minus P, right? So 500 times 0.88, which is 440, which is definitely also greater than or equal to 10. So using a normal distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. So I've got my curve, right? And so my mean here would be 60. Okay, 60 is my mean because remember I find my mean, right? I find my mean with N times P. So 60 is my mean. This is an attempt at a normal curve. My standard deviation is going to be 7.27. Remember my standard deviation is N times P times 1 minus P. Okay, so that is 7.2. I'm going down here at 50 or less. And so if I want to find this, I can calculate my z-score, because we're going to do that all the time out of habit, right? And I'm going to divide that by 7.27. So my z-score here is negative 1.38. And then you would need to show your work for how you're doing this on your calculator, or you need to state that you're using Table A to find the area. So I'm going to go normal, CDF, and in this case, my upper, because I'm going down, would be my z-score, negative 1.38. My lower is negative, big, fat, giant number. My mean is going to be 0 because I use my standard curve, standard deviation of 1, and I get an area of 0.084. Okay, so you'll also need to watch your geometric video, and I will put up some practice binomials on Google Classroom. And the answer to your joke of why did the girl wear glasses during math class is because it improves division.